The squeeze theorem says that if you have a function g that is squeezed in between two functions f and h, or sandwiched in between them, sometimes this theorem is called the sandwich theorem, and this is true, and there's some technical conditions there. It's true for all x in an open interval containing b except possibly at b. I'll explain that in a minute. And that you have that the limit of f and the limit of h are the same, then the function that gets squeezed in between f and h has to have the same limit. Okay, so let's illustrate that. Here's the idea. We have a function. So say we have some kind of a function here, f, y equals f of x, that has a limit at b of L. So this would be a picture of limit as x goes to b of f of x is equal to L. And you have some other function h that has the same limit. So here's y equals h of x. And suppose then that g is in between them. Now, it doesn't have to be in between them everywhere. It just has to be in between them on some open interval around b. That is, so that you're on both sides of b, so that you can take the two-sided limit, and it's close. And then remember, when we're taking a limit, we don't care what the value of the function is at b, so that's why we've accepted b. So that's what the special conditions there were about. But look at what would happen if g has to be in between here. It sure looks like, from both directions, g has to have the same limit. And we can actually prove that. Here's a proof. Since f of x is less than or equal to g of x is less than or equal to h of x, then that has to be true for values of x, as long as we're in that open interval. For values of x that are infinitely close to b, it would have to work. So pick something like b plus alpha. For any infinitesimal alpha, if I plug that in for my x, it would have to work. So that means that g of b plus alpha is between f of b plus alpha and h of b plus alpha. But here's something we know. We know that the limit as x goes to b of f of x is equal to L, right? But how do we find the limit as x goes to b of f of x? We find f of b plus alpha, right? If f of b plus alpha gives you the same value for every infinitesimal, then that's our limit. So that means that for whatever infinitesimal I've got, f of b plus alpha has to be equal to L. Well, the same thing's true for h of b plus alpha, because that also has the limit L at b, or h does, so h of b plus alpha must be equal to L. Well, that means that g of b plus alpha is between L and L. Well, that means it's got to be L. So g of b plus alpha is equal to L. Now that's true for every infinitesimal alpha. And then our definition says, our definition of limit says that as long as g of b plus alpha is equal to L for every infinitesimal alpha, then that is our limit. The limit as x goes to b of g of x is equal to L. Okay, let's look now at an example of how we would use the squeeze theorem. So we'll look at an example. We'll suppose that x squared plus 1 is less than or equal to g of x, which is less than or equal to 2x for all x. Okay, so now our technical conditions there are met. So we have the x squared plus 1 is like our f above, and the 2x is like our h above. So let's find the limit. Let's see what the limits are. let's take the limit as x goes to 1 of x squared plus 1 here on the left. That would be equal to 1 plus alpha squared plus 1, right? If we want to take the limit as x goes to 1, we plug in a 1 plus alpha. So that gives us 1 plus 2 alpha plus alpha squared plus 1, which is 2, right? Because we can throw away our infinitesimals as we approximate there. Well, we can do the same thing on the right-hand side. What is the limit as x goes to 1 of 2x? Well, that would be twice 1 plus alpha. Again, we plug in 1 plus alpha for the x. So that gives us 2 plus 2 alpha, and when we approximate, that gives us 2. So that means our limit of f, the x squared plus 1, is 2. The limit of h, the 2x, that's also 2. So all the hypotheses of our theorem are met. So by the squeeze theorem, g must be squeezed in to where it also goes to 2. So the limit as x goes to 1 of g of x is equal to 2. And that's how we apply the squeeze theorem. Now there's another way to write this up. Let me turn the page and show you an alternate way of writing this up. So again, we want to find limit as x goes to 1 of g of x, and we find that by plugging in 1 plus alpha for x. Now we also know that g of x is between x squared plus 1 and 2x for every x. That was our inequality that we were given. So if I want to find g of 1 plus alpha, I might as well plug 1 plus alpha in for x in this inequality. So that's really an application of the transfer principle. Again, so in other words, I'm really following what we did in the proof here to show you that you can write these problems up in that same way. So again, I replace my x by 1 plus alpha. Now what do I have on the left? 1 plus 2 alpha plus alpha squared plus 1. And what do I have on the right? 2 plus 2 alpha. So when I approximate on the left, I've got 2. And on the right, I've got 2. So that means g of 1 plus alpha must be equal to 2. But as we said above, that is the limit as x goes to 1 of g of x. So we found our limit. It's 2. So again, that's an alternate way to write up the solution to that example.